Yes, so I'm going to tell you about the relationship between learning and refutation. Somehow the mantra is that if you want to get people interested in some topic, you must relate it to learning. So I'm going to relate refutation to learning and hope that like 10 times more people work on refutation now. So this is a joint work with Roy Livni, who is a postdoc at Princeton. And he actually specifically reminded me to tell you all that he is the best Israeli co-author I have had. All right, so let's begin. So there are two problems in the title. I'm going to tell you about the two problems and then what the relationship between them is and then prove it. Okay, it's a very simple talk. So first I'm going to tell you about what agnostic learning is. Maybe all of you already know it, but I'm going to go over it again. So the setting is that you have a distribution, and the distribution is over examples, which we will think of as coming from 0, 1 to the n, even though basically the domain is not really important. And the labels we're going to think of as coming from plus or minus 1. Okay, so these are Boolean valued examples, if you will. So so you can think of them as these examples as defining equations like this. You're like hunting for some function h, such that at ith example xi, the output of h is equal to bi. Okay, so xi comma bi is the example that you saw, and what you're looking after, what you're looking for is finding an h from some given class script h that satisfies as many of these equations as possible. Okay, so concretely, I'm going to define this measure as so the optimal the optimality of a certain function. The optimality of a certain class script h for a distribution D, I'm going to define as follows. It's the maximum correlation any function in the class script h achieves with the right-hand side of these equations when they are chosen according to a distribution D. Okay, so just so that we're on the same page, if all these equations were sort of satisfied by some fixed function small h in the class script h, then opt would be 1. But in general, that may not be true. There could be noise, and let's say only 51% of the equations are satisfied. In that case, because I'm measuring correlations here, opt would be 0.02. Okay, so in general, this number is going to be between 0 and 1. And yeah, so what is my goal? What's my algorithmic goal here? I'm going to, I want to see as few examples as possible. Let's say m examples drawn according to a distribution D. They are IID examples, and I want to construct some small h, let's say from the class script h, which sort of tries to maximize the correlation with the right-hand sides. So my goal, just to be concrete, would be to get let's say within 0.01 of the optimal correlation value. Okay, so this problem is called agnostic learning whatever script h over the distribution D. The one thing I want to point out is that I can relax this requirement of the small h coming from the script h, and in fact allow you to return any hypothesis at all. Okay, so you can give me any function f, so long as it predicts the right-hand sides of the equations that I see well enough. Okay, so in some sense I do not restrict you even to output a function from my own class. This is sort of called as improper learning in learning theoretic settings, and somehow actually it is known to add a lot of power to the algorithm designer. Okay, great. So I'm not sort of going to survey anything about agnostic learning, but just a few comments are in order before I proceed. So in some sense, this was a model proposed way far back in 1994 by Kern, Shapira, and Selly. It's like the standard model for supervised learning under noisy settings. So you want to model, there is some noise in the examples, noise in the labels, and you still want to sort of have your algorithm learn something meaningful. Okay, and so there are like many influential works, and as I said, improper learning is fine. So we are not actually restricted to returning hypotheses from the same class. And the point is that sort of years of influential work actually have generated a few very general techniques which are good for this kind of a problem. So you just want to throw away some words if you already know them. It's interesting. Otherwise, it's not a big deal. So there are these general methods called as polynomial regression, which is like you take your function class, approximate by polynomial, and then polynomial regression happens to be an easy technique. So you can sort of do agnostic learning with this trick. To show that polynomials are good to approximate your class, you can use Fourier analysis, some of which occurred in, at least Fourier analysis in some form occurred in Avishai's talk. Again, not important for this talk. The one important point I want to make, however, is the following. So for any learning problem, there is something called as a sample complexity, which is like how many samples do you need to see before you can return something correctly with high probability, something that has low error. And so if I don't care about efficiency of the algorithm, then sample complexity is basically the number of samples I need to see to sort of do good. And it turns out that when actually we are looking for efficient learning algorithms, let's say even in the agnostic setting, then whenever they are possible, somehow it actually so happens that the number of samples that we require for an efficient algorithm to succeed is markedly higher than the samples required, for the information theoretic, like inefficient algorithm to succeed. So somehow there is sort of inherent sample complexity cost of efficiency. Okay, good. So now I want to define imperfect refutation. Sorry, this slide sort of puts you a lot of information all together, but I'll parse I'll parse all of it out. So the setting is actually quite a bit similar. We again have a distribution, okay, and the distribution is still on examples and labels, okay. But the goal of the algorithm here is actually much weaker than before, okay? So the goal of the algorithm is actually to just output a single bit. So it either outputs structure or noise, okay? And so what is the guarantee for correctness? The correctness guarantee is that suppose the labels in the distribution D are uniform plus minus 1 bits independent of the examples. In other words, labels are just complete garbage, okay? In that setting, your algorithm must output noise with, let's say, overwhelmingly high probability. Okay, so it should correctly identify that the labels were complete garbage. Okay. On the other hand, if there is some h in your script h in your class which achieves, let's say, a large correlation, let's say whatever, some non-trivially large correlation like 0.01 with the right-hand sides, the labels from your distribution, then the algorithm should correctly output structure again with, let's say, overwhelmingly high probability. Okay. So in other words, I'm asking my algorithm to only perform a distinguishing task. Identify if the labels are like complete garbage or there is some structure in labels, and the structure is defined with respect to the class I'm trying to learn. Okay? So notice that I'm not asking you to figure out the hypothesis that correlates with the right-hand side. So it's a weaker task than learning in general, okay? Or at least potentially weaker, even though the main punchline is that it's not. So I'm going to call this problem strong imperfect refutation, and again the words don't matter. I'm using so many words to define this problem because if I call it just refutation, which is what I intended to before, then it actually, so in some sense that's, so the motivation for this, and hopefully I'll come to that later, comes from refuting random constraint satisfaction problems. In that setting, there are some differences. In particular, the error is one-sided, so that this 0.99 actually becomes 1. And the distribution is somewhat specialized, etc., etc. But like philosophically, really that problem and this problem are really the same, except like this is slightly more general. Just so that there is no confusion with CSP refutation, I'm going to call it strong imperfect refutation. Okay? So strong sort of here refers to the fact that the correlation is not 1, it's like 0.01. So in some sense, I want to succeed in a stronger regime. The imperfect actually refers to this not being 1 but 0.99. Okay? Just in case there is some reason for the words. Great. And just like before, I want to make like a few simple comments about this strong imperfect refutation problem. At least if I remove the imperfect part from this, then this was a problem again classically considered in this landmark paper by Uri Feiger, where he related average case complexity to worst case hardness of approximation. And actually, as I mentioned before, it has been actually very well studied in the context of random constraint satisfaction problems. If you don't know what they are or how they relate to here, it's not important. You already know the problem, so that's enough for us. But the point I want to make is that this type of problem is actually central to average case complexity. And in fact, hardness assumptions about such problems actually form the core in some sense. It's one of the one or two very important hardness assumptions used to prove hardness results in average case complexity. Okay? And again, just like agnostic learning before, people have actually identified fairly general tricks that actually work here. And the nice thing is that they are very different from the kind of tricks that we know for agnostic learning. So they actually happen to be spectral methods or more generally semi-definite programming. Okay? And just to tell you the same point again, efficient refutation, just like efficient agnostic learning, as I said before, seems to require way more samples than the information theoretic requirement. So in some sense, there is still this cost of efficiency that we pay even for the refutation problem, even though it appears like a simpler problem. Okay? And in this regime, it turns out that in fact there are concrete conjectures about this gap between the sample complexity required for efficient refutation versus sample complexity required for potentially inefficient refutation. So in particular, if you know something about this, then there is this concrete hypothesis called as Feiger's hypothesis, which is one hardness assumption I was mentioning before. Okay? So are there any questions about the problems I'm going to talk about? Okay, great. So there are just two problems that we defined, studied, and think are natural, cool, nice. And the question I want to ask today is, are these problems related? And one direction is really simple. In some sense, I already hinted at in the way I defined the problem. Clearly, learning seems to be enough to solve the refutation problem. Like if I can actually find a function from my class that predicts the right-hand sides, then that already certifies that the right-hand sides cannot be random, right? Like they cannot be IID, random, etc. So I can definitely use a learning algorithm to perform the refutation task. Okay? So this connection, even though it's like simple and trivial, in some sense it actually underlies this breakthrough result of Danieli et al. Who sort of used Feige's hypothesis, which is like hardness of certain constraint satisfaction refutation problems, to establish the first hardness results for improper pack learning. Okay? So again, I hinted at this before, but this freedom that you don't need to return a hypothesis which is from the same class that you're learning turns out to be quite powerful, which on the flip side means that proving lower bounds against this powerful class of algorithms becomes hard. And in some sense, for a long time, we did not know how to prove improper learning hardness results until Danieli et al. Actually made this simple connection between refutation. Like in some sense, this is somewhat implicit, but they basically showed that refuting certain CSPs can be reduced to pack learning some natural problems like DNFs. And then they used standard hardness assumptions about refutation to derive hardness of improper learning results. Okay? So the easy direction in some sense is clear already by the way we discussed. And the main result of this talk is that in fact the other direction also holds, that in fact refutation is enough to do agnostic learning. Okay? So I'm going to reiterate, even though it's like everything is simple, I'm claiming that a subroutine that actually allows you to distinguish between labels being completely random versus labels being labels showing some correlation with a function in your class is actually enough to figure out what function it is. Okay? Are there any questions about the results so far? Yes? No. It's going to be very important that we don't, yeah. So this is in fact, this is about agnostic learning with potentially a hypothesis that is not in your class. In fact, proper learning could be much harder. Okay, I'll potentially come to that towards the end depending on how much time I have. Great. So that's the result I'm going to present today. And it turns out that when there are beautiful theorems, multiple people actually come to them via independent routes. So it turns out that this theorem was very recently discovered in a different form by Salil. And in some sense, the proof in the end turns out to be essentially the same. So I'm going to essentially present to you Salil's proof. But the slight difference is that Salil talked about the setting of pack learning, which is like non-noisy setting. And since it's a characterization, the notion of refutation that relates to pack learning has to be necessarily different. And it turns out that the strong actually changes to weak. And again, not super important what these things are, but basically there is some natural variant of the refutation definition that I talked about before that turns out to be equivalent to pack learning. And we're just going to see the agnostic counterpart of this. Okay, great. So I want to sort of now go back to this point that Greg mentioned in his summary, this relationship to computational sample complexity. So for this, let's try to understand the following question. Suppose I don't care about this efficiency part here. Okay. Suppose I just want to understand how does agnostic learning relate to imperfect strong refutation. Okay. So are these two problems equivalent? In particular, does strong imperfect refutation imply agnostic learning if I don't care about efficiency? Okay. It turns out that this is true. It's a theorem due to Bartlett and Mendelssohn from like way long ago. And in some sense, they did not phrase it this way, of course. So I'm going to tell you why, in some sense, what they showed. And in some sense, it's a fundamental theorem in statistical learning, what they really showed. And this is just a reinterpretation of their theorem. Okay? But it would be nice because it would give you one nice vantage point to actually interpret what we're going to show today. So what they actually considered is a notion called as Rademacher complexity. If you've not seen this before, in some sense, it's a more general analog of VC dimension that characterizes sample complexity of a learning problem. Okay, so say you have a function class H, okay, and say you have a distribution D. So this distribution, in general, is over examples and labels, etc. Okay, so in some sense, you're trying to agnostically learn this function class script H over the distribution D. Okay. And say you have m IID examples from this distribution, okay? Then I'm going to define this quantity as Rm of H as follows. I'm going to draw x1, x2, xm, the example part from the distribution D, Okay, so I took m examples, I like stripped them of the labels and look at the example parts. For the labels, in some sense, I replaced the actual labels generated according to D by completely uniform and independent plus minus 1 random variables. These are called as Rademacher random variables, and that's why the name Rademacher complexity. And then I consider the following quantity. I find out, so I basically take any function h from my class script h, and I compute the correlation of h when evaluated over this x1 through xm, the m examples, with completely random noise sigma i's. Okay? And I basically find out the maximum correlation of any function in my class to this complete garbage. Okay? And then I just take expectation over the examples and the sigma i's, the randomness of the sigma i's. What does this, in some sense intuitively, what is this quantity trying to measure? It's basically trying to understand, over your distribution, so over the kind of examples that can appear in your distribution, what is the maximum correlation that in some sense any function in your class can have to complete garbage, like completely random noise. In some sense this is bad, right? Like if I'm trying to learn, I know that the true correlation of any function in my class to complete garbage is supposed to be 0. So in some sense I would want this quantity to be small if I expect to learn. I need to identify that the labels are complete garbage, right? So this quantity in some sense is some handle on it. Okay? This is trying to understand what is the maximum correlation of any function in your class to completely random noise. Okay? So again, this is somewhat non-standard way to talk about it, but I'm gonna do this because it sort of fits in nicely with what I'm going to tell you today. So I'm going to define the Rademacher complexity of a class script h over a distribution D with over a distribution D as the smallest number m, such that this correlation, expected supremum of the correlation with noise is smaller than some 0.01. Okay? Is the definition clear? Good. So the first thing I'm going to observe is that in some sense almost by definition this is trying to get at the problem of testing between completely random noise and like some tiny bit of correlation in the labels. Okay? And why is that? Well, here is a completely stupid algorithm to do refutation. Just go over every function in your class, find out the correlation with some m examples that you have actually drawn, and if the correlation is smaller than 0.001 or 0.01, then reject, like say that it is noise. Otherwise call it structure. So the Rademacher complexity says that if you actually took enough number of examples to make Rm of h at most 0.01, then this inefficient stupid tester will actually succeed, right? So in some sense it's in some sense like just an analysis of this tester. Okay? So I want to point out that if you don't care about efficiency, then Rademacher complexity is nothing but basically the analysis of a stupid refuter. Okay? Great. So so that's what we already saw. What Bartlett-Mendelson showed is that in fact h is agnostically learnable on distribution D with m samples if and only if this Rm of h quantity, the same quantity we saw on the previous slide, is at most 0.01. So in some sense what actually allows you to refute also allows you to learn. Okay? So this I'm going to interpret as the theorem I told you before, that if you don't care about efficiency, then agnostic learning actually can be done by just refuting. Okay? So so in this spirit I'm going to define refutation complexity, which I'm going to interpret as computationally bounded analog of Rademacher complexity, as basically the smallest m for which there is an efficient structure versus noise tester. Okay? If I didn't care about efficiency, then the inefficient tester that I talked about before actually works, and Rademacher complexity is actually exactly that. So if I impose efficiency, I'm going to call that small m refutation complexity, and now the theorem that we already discussed before. Basically the point is that this characterizes the sample complexity of efficient agnostic learning. Okay? Great. So if there are no questions, I can tell you the proof. How much time do I have? Okay, that should be enough for the proof. Okay, great. So in the remaining minutes, I'm going to basically tell you the proof, and the proof is really simple. In some sense, the whole contribution is to basically just define. I think this really nice definition, at least something that I feel is really nice. Seems like a natural, nice analog of computationally bounded Rademacher complexity. The proof itself is in some sense what you would expect, like in some sense the most natural thing you would do, and I'm going to tell you what it's going to be. So we already saw that in some sense one direction is easy. So really we are looking for proving the following claim, that efficient, strong, imperfect refutation implies efficient agnostic learning. Okay? So in some sense, what do I want to do? I want to take a structure versus noise tester or a refuter, okay, and convert it into a learning algorithm. Right? Great. So I'm going to do this in 2 steps. Okay? And in some sense, if you've taken like the first class in learning theory, then this is something which is like the most natural thing to do. So in step 1, what I'm going to do is use a structure versus noise tester to come up with what is called as a weak learner. Okay? So in agnostic learning, we are trying to get a hypothesis whose correlation with the right-hand sides is as close to opt as possible. Okay? A weak learner doesn't actually get that. Okay? So it doesn't get correlation which is opt minus 0.01 or whatever. It actually gets some, some tiny number gamma times this opt. Okay? So that's what I'm going to call a weak learner. Okay? So it's not going to accomplish the goal I want. It's going to get me somewhat close to that goal. Okay? And then it turns out that there is a off-the-shelf method called as boosting. Again, potentially almost everybody is familiar with that. There is a boosting also that works in agnostic or noisy setting. But there is an off-the-shelf method that takes a weak learner and converts it into a strong or like actual agnostic learner. Okay? So in some sense, this second step is completely off the shelf, and we are going to apply some known black box boosting algorithms. So all my task is going to be to get something called as a weak learner. Okay? And again, in this argument, there's not going to be like great innovation. It's going to be something, if you've seen like the Yao's argument for next bit predictability and relationship to pseudo-randomness, there's going to be the very similar hybrid argument that happens in that work. And I'm going to spell it out very explicitly now. Okay. So how does this step work? So recall that's the refutation algorithm definition, and I want to sort of give you the weak agnostic learner definition that I was telling you before. So I want to look at IID labeled examples, let's say m in number, from the distribution D, again on example comma labels. Okay? And what I want to do is find some function h, okay, whose correlation with the right-hand sides of this distribution D is gamma, some tiny like this. Okay, it's tiny but not that tiny hopefully. Gamma times whatever is the best possible correlation I could get up to some tiny additive error. Okay, that's what I'm going to call a weak learner. If this gamma weren't present and this alpha were 0.01, then it's a strong learner. I'm just allowing some more slack here. Okay? Great. So what I want to do is somehow use the refutation algorithm to get like a weak agnostic learner. Okay? And in some sense, like I only have one algorithm, one box in front of me, the refutation algorithm. So all I can in some sense hope to do is feed this box different kinds of inputs and hope that something that I want comes out of it. Okay? So that's what I'm going to do. I somehow, so if I want, so what I want to do is like take the code for the refuter, okay, and get a code, like get some description of this function h that I'm after. Okay, so I want to get some method to compute h at any input x. Okay, so I'm going to somehow take this input x that I want to compute this weak learner at, and somehow feed it as an input to the refutation algorithm. Okay, so the idea is really simple. The refutation algorithm, remember, takes like m IID examples as input. Okay, for any index I can sort of kill the xi yi that I get from the examples and replace it by the x I want to actually compute the function at. Okay, so remember, like m IID examples are what is the natural input to the refutation algorithm. For any I can replace the ith example point xi by the x that I actually want to compute this weak learner at. So this is like I'm trying to design the code now. Okay, and now, in fact, I'm going to make one more change. Okay, for any I, what I'm going to do is for every example that comes before I in the list, I'm going to replace the actual label that I see by a completely uniform and independent label. Okay, so in other words, for whatever comes before I'm going to randomize the labels. At ith point, I'm going to sort of feed in the x I want to compute the function at, and let's say replace the right-hand side with some chosen bit b. Okay, for any given I, this is what I can do, right? Like randomize the labels that comes before, feed in the example point that I care about at ith point, and let the rest of them remain the same. Okay, so this is like some hybrid distribution where some labels are randomized and some other labels are not randomized, like they are the original labels. Okay. So here's the main, like here's in some sense the only observation. If I randomize nothing, then I know that the distribution has structure, right? In some sense, that's what I'm trying to learn. So if I randomize nothing, if the right-hand sides are replaced, if they're not replaced by uniformly random bits, then most of the time the refutation algorithm should output structure. And if I like make structure equal to 1, then the expected value of this algorithm is going to be close to 1. Okay? On the other hand, if I randomize everything, then I know by correctness of the refutation algorithm that it should correctly identify that the right-hand sides were completely random. So it should output basically noise most of the time. Noise means 0, so the expectation should be small. Okay? So now here is the simple observation. Like imagine that I sort of one by one replace the right hand, like the labels by random basically one by one randomize the labels. I know that on the one end there is a large correlation, like large expectation. On the other side there is a small expectation. So in some sense there must be some change which is like somewhat sensitive to randomizing. Like there should be some bit at least which if I switch from the actual label to the randomized label, then I drop in expectation by at least some 1/m fraction. So this bit in some sense has some information about whether I am using the right label or not. Okay? So you can imagine that I can somehow use it to construct a weak learner that will correlate with the actual right-hand side with some 1/m correlation. And that's sort of the only idea. So if you just work out what you should do, like in some sense there is only one right thing to do. If you work that out, you would basically end up proving that there is some basically natural weak learning candidate from here that will have correlation like roughly 1/m. Okay? And that's it. You get a weak learner, you apply an off-the-shelf boosting algorithm, you get a strong learner, you're done. Okay, so I want to summarize and end. There are two natural problems. One of them is learning, so that's nice. And it turns out that they turn out to be equivalent, so that's great. And the nice thing is that it also, this sort of connection naturally gives us an analog of computationally bounded Rademacher complexity. That's useful potentially. And the one thing in some sense, a priori could be surprising is that a very weak kind of oracle access to the function class you're trying to learn turns out to be enough to agnostically learn it. Just this tester of structure versus noise, like completely random labels while distinguishing between completely random labels and somewhat correlated right-hand sides. This distinguishing algorithm turns out to be enough to do learning. At first it appeared somewhat surprising to me, but it happens to be true. It would have been really great if I had like a spectacular application of using a refutation algorithm to get a learning algorithm, but I haven't found that yet. Maybe you can. The hope, or in some sense the nice thing here that could potentially be helpful is that the techniques that have been developed for refutation problems in general seem to be very different from the techniques that have been employed in agnostic learning literature. So in some sense it won't be very surprising if some of these hammers turn out to be useful in learning algorithm design. Again, I don't have a great example so far, so okay, so this point I already made before, that this is a characterization of improper learning, and let me not dwell on that. Thank you so much for your attention. So are you, okay, so I want to understand, are you trying to talk about the correct factor in sample complexity or the correct factor in time complexity? So this connection is actually, so I only sort of talked about efficient algorithm just so that things are somewhat simple, but it's actually, the connection is somewhat more fine-grained than this. So in some sense you can define refutation complexity at every running time. Like you can fix a running time T of n and define, and then the translation sort of, basically preserves the running time up to, I think, log factors. I mean, I maybe don't recall it correctly, but either constant factors or log factors, so like something very mild. So at least in time complexity, it appears like the translation is fairly tight. And my sense is that in sample complexity, it is even tighter. It's like there, I think it is really just within constants. So if you can refute with certain sample complexity in certain time, then you can learn in some, let's say, log factor extra time and constant factor extra number of samples. So